Okay, so the video for lesson 6, we're big change of pace here. With lesson 5 we were Gil's Alder. Lesson 6 we're here. And I'm going to ask you, what's the big picture for this lesson? What's the big picture? Two reactions. Substitution and dehydration, which is a subtype of elimination. Okay? So let's talk about lesson 6, substitution reactions. What we have for substitution reaction is, these are substitutions and dehydrations of alcohols, okay? So we have for substitution reactions, we've got a nucleophile, which in this case is going to be, in every case actually in this chapter, is going to be a halide. Or I should say every case in this lesson is going to be halide, right? So the root reaction that we have here, or the workhorse reaction, is that and that, which gives us, right? I sort of draw it upside down to remind you that we get inversion of configuration. If it's SN2, we get inversion of configuration. All right, so for the first couple sections, we talk about how to make this happen. Well, it turns out with primary alcohols, that is, if this is right, and those other two things are just hydrogens, this is not a good leaving group, not at all, right? So in order to make this happen, we're going to have to do something to make this a good leaving group. And I think in every case, we're going to do this. We're going to, you know what, I'm just going to put a box around it. I'm going to let you figure out what we're doing to make it a good leaving group. Okay? Put a box around it. It's not going to be an OH, all right? I'm just saying, well, I thought about putting a star there, but sometimes we do star for anti-bonding, or what's the star mean, you know? So we do something to it to make it a good leaving group, and then at that point, we get halide that comes in. Okay, and after it's a good leaving group, that's good. All right, so primary is going to go SN2. All right, secondary is not going to go SN2. Secondary, we're going to have the simple, and this is probably the workhorse reaction for this. I'm going to use bromide here, for example. Okay, I'm only going to draw one lone pair of electrons on there. This is HBr. I'm just go ahead and separate them out. What's going to happen here is, boom, right? And what do we get there? What do you see here? What do you see there? I know, my question is too broad. You tell me. Look at that. Think about it. What could I be asking? Number one, you see water. Number two, you see a good leaving group, right? Why is it a good leaving group? Because it's so stable on its own, right? Okay, so if these guys go off, it's just simply water. And that's what happens here. Boom. And then we get, okay, what do you see here? A secondary carbocation. Please try to answer those questions. I know my questions are very broad, but try to think, what could I be asking? All right? Secondary carbocation. All right, what's going to happen here now? Boom. Okay? Is that SN1 or SN2? Right? It's SN1 because we had the leaving group that left on its own. I admit we had to push it. I'm sorry. We did have to push it by making it a good leaving group. But it left without the nucleophile coming in first. All right? So this happens in 2 steps. This is the first step of the... I said 2 steps. Is that confusing? Right? 1, 2, 3. I'm still going to call it a 2-step reaction. Because all we're doing here is just proton transfer. We're just getting this guy ready to go. All right? That's a matter of semantics, I suppose. But the real reaction that we're worried about here is 2 steps. These 2 things right here. Okay? And by the way, these are equilibria too. This is not an irreversible reaction. I told you I was going to be a little bit liberal with those arrows. Okay? And then the third one, the tertiary, is going to look like this. I'm going to go ahead and make that HBr like that this time. This time over here, I drew them as separate. This time I'll draw them as together. It's an equivalent issue, right? Argue with me on that in class, and I'll convince you that this is two ways of drawing the same thing. All right, so that goes there, but this time I can't just draw the one arrow. what arrow comes next, obviously. I'm sorry, which is demanded now? That one. Boom. Right? A bunch of you got that right in this last quiz. Maybe we've seen it a couple times. I've seen a lot of people get that right. This is critical. So what do we get here then? Alright? Plus Br. There are 4 lone pairs of electrons on there. I'm just going to draw the one if you don't mind. I'm just going to draw that one. What do you see here? Water as a leaving group, right? So if this guy goes off, it's just water. And that's what happens. Boom. Did it bother you that I didn't draw water here? So water left, and I didn't draw it again. Why not? It's just the solvent. Why didn't I draw the water there? Because it's just the solvent. Okay, I did draw it here because I thought somebody might be wondering where it went. So what happens now? Well, 2 possibilities. Water can come in, or that can come in. Which happens? I'm going to leave that as a question. Water or bromide? Okay, and that is another S. How do you spell S? SN1. Okay, so that's the first part of lesson 6. The next part of lesson 6 is dehydrations, and the general mechanism for that is this. The very, very general mechanism, I guess, for that would be well, this would be antiperiplanar, right? That would come in here, and this would go there. Right? That would be that would be too general, I think, right? Because we're not going to be. This would be basic, and I go, okay, it's too general. Let's do this in terms of acidic. Let's do this in acidic conditions. And I'd like you to prove to yourself that they're equivalent, right? Different conditions, but they end up giving us the same products. So there's another hydrogen on here, of course, right? Okay. So let's do this under acidic conditions now. Okay, I'm looking at page I'm doing section 11.4 now, which is the last section of this lesson. And okay. Simplest case scenario. And I think we're going to do H2SO4 each time. Nitric acid may work on this, but no, I think every example in the book is going to be H2SO4. That's good. That keeps our world simple. I think every example in... Wow, it's a long section, isn't it? Alright, that's not true. On page 498, there's another example. Let's do this one for now, okay? So this is the same thing as H is SO4H, right? There's our H2SO4. This guy comes here, boom, and he goes here. To the S, right? To the S. So we get, right? And sometime, I told you the other day that, who was talking to me about this? And I said that this proton gets abstracted by a base. Oh, it was Becca. This proton gets abstracted by a base. Which base? Well, you know, I argued with Bruce about this. It turns out on page 497 or 496, she uses the same base I would use, and that's water. In other places, she uses the conjugate base of this, right? S. There's our SO4 minus, right? Or HO4H minus bisulfate, okay? So sometimes she'll use that. In this case, in this chapter, she's going to use that, which I think is correct. And that goes there, and that goes there. And this is your alkene. Okay? So this is acid catalyzed, how do you spell catalyzed? Dehydration. Alright, acid catalyzed dehydration. And then a very similar reaction happens on page 498. page 498. Top of page 498. And I'm going to let you look at that on your own. Okay, so that's lesson 6. What we had for lesson 6 was substitution and dehydration. And in both cases, we had to make this leaving group better. In both cases, we had leaving group, right? We started out here, and we said this is the general, very, very general terms. That's what it would be, except hydroxide's a terrible leaving group. So let's do something to it. Let's do a magic reaction. And then we cap that and make it a better leaving group. How? Well, in most cases, well, in the simplest case, we simply protonate it. If you protonate that, the leaving group is water. If you don't protonate it, the leaving group is... Let me ask that question again. You please answer it. If we don't protonate this, what is the leaving group? Is that a good leaving group? If we do protonate it, what is the leaving group? Is that a good leaving group? Okay, those are really I think the critical questions. So hopefully that's helpful. I admit that's a fairly low resolution overview of lesson 6.